The research paper discusses the scaling law with learning rate annealing for neural language models. It proposes an equation that describes the cross-entropy loss curves, taking into account both forward scaling and the additional loss drop brought by learning rate annealing. This formulation can accurately predict the loss of language model training at any given step and across any learning rate scheduler. The paper builds upon the chinchilla scaling law by introducing an additional learning rate annealing term. It also provides a detailed explanation of the learning rate schedule and its influence on the loss during training. The authors demonstrate the derivation of the scaling law and its extension to model size. They apply the equation to verify and explain previous study conclusions, showing its potential to democratize scaling law fitting and predicting in developing large language models. The paper explores the relationship between learning rate schedules, LRS, and validation loss in large language models, focusing on the impact of different LRS on model performance. It presents a universal loss curve equation that can accurately predict the validation loss trends for various LRS, including cosine, constant, WSD, and even strange LRS. This equation is a generalized form of the chinchilla scaling law, offering significant savings in computational costs for fitting and prediction. The proposed equation, L equals 2.628 plus 0.429 s caret, 0.550, 0.412 s squared, is derived from experiments with different LRS and is highly precise in predicting the trend of loss changes as the learning rate varies. The results show that the mean prediction errors across various LRS are low, approximately 0.2%. The study also highlights the importance of balancing the forward area and annealing area in the LRS, which is crucial for achieving optimal model performance. By consolidating resources, the paper simplifies the process of understanding the crux of loss drop, LR schedule, and LR annealing. In addition to providing a comprehensive analysis of LRS, the paper compares its equation with the typical chinchilla scaling law, demonstrating that the chinchilla scaling law describes special cases of the proposed equation. This indicates that the proposed equation is a more general form of the chinchilla scaling law, further democratizing the fitting and prediction of scaling laws. The paper's findings contribute to a deeper understanding of how LRS influences model performance and could guide researchers in selecting critical LRS in advance using the prediction equation. Overall, the research offers novel insights into the interplay between LRS and validation loss, advancing the field of large language models and their optimization techniques. The paper discusses the relationship between learning rate, gradient norm, and validation loss in neural network optimization. It is observed that the curve shapes of these three variables exhibit a high degree of similarity across various learning rate schedules, LRS. This suggests an implicit connection between learning rate and loss, with gradient norm acting as a bridge. The study also explores the concept of learning rate annealing, which involves reducing the learning rate over training iterations to improve model performance and stability. The paper introduces a novel equation to describe the loss changes during learning rate annealing, taking into account the effects of both scaling laws and the extra loss changes brought by annealing. The proposed equation is in the form of Ls equals L0 plus As caret, alpha, F, eta, where Ls represents the validation loss at step S. L0 is the initial loss. A is a constant, alpha is a hyperparameter, S is the total amount of neural network parameter changes, and F, eta, denotes the extra loss change brought by learning rate annealing. The paper further investigates the phenomenon of momentum in learning rate annealing, where the validation loss lags behind the learning rate in terms of response time. This lag is demonstrated through special learning rate schedules designed to test the momentum property of learning rate annealing. The findings suggest that the delay between the learning rate and validation loss increases with the number of delay steps in both annealing and rewarm-up processes. Moreover, the paper discusses the concept of training discount in annealing, which refers to the faster decline of loss drop during learning rate annealing due to decreasing gradient norms. This phenomenon is captured by modifying the loss equation to include a discount factor, resulting in Ls equals L0 plus As caret, alpha, 1F, eta. This modified equation better reflects the actual loss changes during learning rate annealing. In conclusion, the paper presents a comprehensive analysis of the interplay between learning rate, gradient norm, and validation loss in neural network optimization. By introducing novel equations to describe loss changes during learning rate annealing and exploring the momentum and training discount phenomena, the study provides new insights into the optimization process of large language models. The paper explores the relationship between learning rate schedulers and the loss curves in large language model pre-training. It introduces a novel equation to describe this relationship, which is derived from empirical observations of loss drop brought by learning rate annealing. The equation, ELS equals L0 plus AS1 CS2 alpha S, captures the balance between S1 and S2, where S1 represents the cumulative sum of learning rates and S2 represents the cumulative sum of learning rate annealing momentum. The equation demonstrates robust applicability and generalization across various learning rate schedulers, including those with multiple rewarm-up stages. The paper also discusses the delay phenomenon between learning rate and validation loss, observing that the turning point of validation loss occurs later than the turning point of learning rate. This delay is attributed to the momentum in learning rate annealing, which affects the following loss curve for a few steps. The authors define f, eta, equals CS2 as a function to quantify this momentum, with lambda representing the decay factor and S2 as the sum of weighted learning rate annealing. The experimental setups involve training a 594M non-embedding parameters llama architecture-like model from scratch, using the FineWeb dataset for training and Red Pajama CC for validation. The authors adopt the AtomW optimizer with specific hyperparameters and conduct experiments on different total steps and model sizes to validate the equation's applicability across different experimental settings. The findings suggest that the loss drop brought by learning rate annealing scales with both annealing steps and model size, implying that the annealing area S2 in the equation increases when the model size n becomes large. The authors suppose there is a simple relationship of S2 proportional n caret gamma, where gamma is a positive constant to be fitted. The research paper presents a comprehensive analysis of the learning rate schedule in large language models, focusing on its impact on training dynamics. It introduces an equation that describes the relationship between the learning rate, step number, and model size to predict validation loss. The equation is derived from experiments involving different model sizes and learning rate schedules. The equation, L, S, n, equals L0 plus AS caret, alpha, plus Bn caret, beta, CS caret, 2, n caret, gamma, demonstrates how the validation loss changes with varying step numbers and model sizes. The S1 item, AS caret, alpha, represents the forward area where the learning rate is stable, while the negative S2 item, CS caret, 2, n caret, gamma, represents the annealing area where the learning rate decreases. The paper verifies and explains several experimental findings using this equation. For instance, it explains why the loss drops more sharply when the learning rate anneals. This is because the negative S2 item has a more significant impact on the overall loss during the annealing stage, leading to a drastic decrease in validation loss. Moreover, the equation is used to predict loss curves for different cycle lengths and minimum learning rates in cosine learning rate schedules. The prediction results align well with previous studies, showing that setting the cosine cycle length as the total steps and the minimum learning rate as nearly zero leads to optimal loss in the end. This is because setting t as the total steps s and a min LR of 0 can make a larger annealing amount and thus a larger annealing area S2, resulting in lower final loss. Additionally, the equation is applied to explain the phenomenon where constant learning rates achieve lower loss than cosine learning rates if small total steps are set, and vice versa. This phenomenon is validated through experiments and curve fitting, demonstrating the accuracy of the proposed equation in describing the training dynamics of large language models. In the context of optimizing the learning rate schedule in neural network training, this study delves into the scaling law function that governs the relationship between the learning rate and validation loss. The proposed equation, derived from the analysis of two key components, the forward area S1 and the annealing area S2, elucidates the trade-off between these two components in terms of the learning rate. This equation is shown to accurately predict the validation loss under different learning rate schedules, including constant, cosine, multi-step cosine, WSD, and 1SQRT annealing methods. The comparison of constant and cosine learning rate schedules reveals that the latter yields a lower validation loss due to its ability to balance the scaling of S1 and S2. This is further validated by the experimental results depicted in Figure 3, which demonstrates the superior performance of cosine LRS over constant LRS. Moreover, the analysis of multi-step cosine and WSD-LRS shows that these strategies can achieve even lower validation loss than cosine LRS, as they aim to increase S1 while marginally reducing S2. This is also supported by the experimental outcomes presented in Figure 3. Furthermore, the study explores the optimal annealing ratio in WSD-LRS, a critical parameter for achieving optimal model performance. As illustrated in Figure 11, the predicted final loss forms a parabola-like curve across various annealing ratios and total training steps, suggesting that a moderate WSD annealing ratio is optimal. This ratio maximizes both S1 and S2, thereby minimizing the overall validation loss. Additionally, the equation can directly predict an optimal annealing ratio for different total steps, eliminating the need for extensive experimentation and resource consumption. Finally, the research investigates the choice of annealing function in WSD-LRS, with a particular focus on 1-SQRT and cosine annealing methods. The findings indicate that 1-SQRT annealing performs better than cosine annealing at lower annealing ratios, 10% and 20%, but underperforms at higher ratios, 50%. This insight is supported by the predictions shown in Figure 12a, highlighting the importance of selecting the appropriate annealing function based on the annealing ratio. In this research, we delve into the intricacies of warm-up then decay learning rate schedulers, focusing on the warm-up phase and its impact on model training outcomes. Our proposed scaling law function is a generalized form of the chinchilla scaling law, capable of predicting full loss curves across various learning rate schedulers. This function not only aligns with typical scaling laws but also provides an explanatory framework for understanding how different annealing methods and ratios affect model performance. Our equation demonstrates that the validation loss can be predicted by analyzing the forward area and annealing area of the learning rate curve. The forward area, which corresponds to the initial learning phase, primarily influences the final model performance. In contrast, the annealing area, associated with the learning rate decay phase, has a smaller impact on the final loss. We apply our equation to explore the relationship between annealing methods and ratios. The results indicate that at a 10% or 20% annealing ratio, the 1-SQRT method outperforms the cosine method, while at a 50% annealing ratio, the cosine method exhibits a lower final loss. This contradicts previous findings suggesting that the order and results of different annealing hold across settings. Our predictions align well with experimental results, underscoring the importance of carefully selecting the annealing strategy to optimize model training outcomes within the warm-up then decay scheduler. Furthermore, we utilize our equation to analyze the continual pre-training process. We find that the number of re-warm-up steps has little impact on the final validation loss, a conclusion supported by Gupta et al., 2023. This is because, given a fixed max LR, when the re-warm-up steps are longer, the annealing area decreases more slowly and the loss curve rises more smoothly, but both final S1 and S2 are quite stable across different re-warm-up steps. Finally, we compare our scaling law function with the chinchilla scaling law. We prove that our equation has no contradiction with typical scaling laws and is a generalized form of the chinchilla scaling law. This is demonstrated through two conditions: 1. Constant LRS, and 2. Other LRS. In the case of constant learning rate scheduler, the annealing area S2 is always 0 and the forward area S1 equals eta max S, where S is the step, and eta max is the maximal learning rate which is constant over steps. Thus, the whole train loss curves becomes Ls equals L0 plus a eta max alpha, S alpha equals L0 plus a, S alpha, which can be easily reduced to the chinchilla scaling law equation. The paper discusses the development of a novel scaling law for large language models, LLMs, that integrates learning rate, LR, annealing. This new scaling law can be universally applicable to various learning rate schedulers, LRS, such as cosine and warm-up step decay, WSD. and is demonstrated to significantly reduce computational costs compared to traditional chinchilla scaling laws. The proposed equation also enables the collection of thousands of fitting points in one full loss curve during training, democratizing the fitting and prediction of scaling laws in LLM pre-training. The authors present a comparative analysis of the computational costs associated with different scaling laws and LRS. They show that adopting their proposed scaling law requires less than 1% of the computational cost required by the chinchilla scaling law, making it more environmentally friendly and carbon efficient. Furthermore, the proposed scaling law can be applied to any given LRS, thereby conserving additional computational resources. The impact of the decay factor lambda in the equation is explored, revealing that a larger decay factor results in longer delay steps. The results illustrate several key insights into the impact of decay factor on the predicted loss curves for 1-square and 1-sqrt annealing methods, as well as the predicted loss curves in different annealing ratios of WSD-LRS. These findings are consistent across both 1-square and 1-sqrt annealing methods. The paper concludes with a discussion on the empirical rule that more fitting points always achieve better fitting results. The proposed equation can use more points and LRS for fitting, such as 30K constant plus 70K cosine. However, it can collect far more fitting points than the typical scaling law with significantly fewer training steps, making it a more efficient and effective approach in LLM pre-training. In the context of learning rate annealing, this study delves into the phenomenon of delay steps and its implications for scaling laws. It is observed that the validation loss decreases more slowly than expected during the annealing phase, which can be attributed to the historical momentum of learning rate, LR, and its scaling laws. The scaling laws are formulated as a function of the ratio of the number of steps in the annealing phase to the total number of steps. This function, S2, captures the historical momentum and is sensitive to the choice of decay factor lambda. A larger lambda retains more historical momentum, leading to longer delay steps. The paper also explores the relationship between the decay factor and the optimal annealing ratio, finding that a larger decay factor tends to favor a higher annealing ratio. Moreover, the authors examine the role of the atom optimizer, discovering that it has little influence on the delay phenomenon. They propose a revised equation for the annealing area S2, incorporating a learning rate weighted coefficient to counteract the tendency to overestimate loss reduction when the learning rate is nearly zero. This revised equation is essential for accurately modeling the scaling laws and understanding the delay phenomenon in learning rate annealing. The researchers explored the effect of modifying the learning rate annealing function, specifically the exponent zeta in L proportional S zeta 2, on the fitting accuracy of the validation loss curve. Although the introduction of zeta provides more nuanced control over the learning rate annealing, the empirical results show that the fitting improvement is marginal compared to the original formulation without the power term zeta. Moreover, the additional complexity introduced by managing negative values of S2 does not justify the slight enhancement. The authors also discussed potential future works, including refining the equation format to forecast the loss with higher accuracy and extending the equation to post-training, which might involve data distribution shift, data mixture, model alignment, and specific downstream evaluations. The authors concluded that the loss curves of neural language models empirically conform to a scaling law with learning rate annealing over training steps, expressed as Ls equals L0 plus AS caret, alpha, 1 CS2. This equation highlights the balance between the forward area and annealing area of learning rate schedulers, offering theoretical verification and explanation for numerous experimental findings of prior studies. The equation is extended to include model size n and is proven to be a generalized form of typical scaling laws. The equation can accurately forecast the loss of language model training at any given step and across any learning rate scheduler, requiring less than 1% of the computational cost required by typical scaling laws to fit language modeling loss. This approach democratizes the fitting and prediction of scaling laws in the development of large language models. The authors referenced various studies on neural scaling laws, including works by Yazaman Bari et al., Ethan Caballero et al., and others, which provide insights into the underlying mechanisms of language model training. The authors also cited studies on continual pre-training of large language models, which demonstrate the importance of refining the equation format to guide the learning rate re-warm-up strategy in continual pre-training. This research explores the impact of learning rate warm-up steps on the performance of language models, particularly in the context of scaling laws. The authors experiment with different numbers of warm-up steps, finding that 500 warm-up steps result in the lowest validation loss compared to 100 or no warm-up steps. This guides the choice of 500 warm-up steps in subsequent experiments. The paper also discusses various experimental setups, including 3 distinct settings: A, B, and C. These setups differ in terms of model size, training and validation datasets, total steps, maximal learning rate, batch size, and tokenizer. The main setup, setting A, uses a model size of 594 M, FineWeb as the training dataset, Red Pajama CC as the validation dataset, 60,000 total steps, a maximal learning rate of 2x10 to the power of 4, 500 warm-up steps, a batch size of 4 M tokens, Llama 3's tokenizer, and a weight decay of 0.1 with gradient clip of 1.0. Settings B and C are variations of this setup, with different model sizes, datasets, and other parameters. The authors use these setups to validate that their equation works across different experimental setups and to consolidate conclusions in fitting and prediction experiments, as well as next-ended scaling law fitting experiments. The results from these experiments are presented in figures 21 and 22, respectively. The paper references several other works, including those on scaling laws for neural language models, stochastic optimization, and continued pre-training of language models. It also highlights the importance of understanding the impact of warm-up steps and learning rate schedules on model performance, as well as the need for further exploration of these factors in future research. This research paper explores the concept of a universal loss curve equation that can accurately predict various forms of unseen learning rate schedules, LRS, in machine learning. The proposed equation, L equals 2.761 plus 0.517 s minus 0.491, 1 minus 0.458 s2, is highly precise in predicting the trend of loss changes as the learning rate varies. This equation was fitted using cosine and constant LRS setups, with mean prediction errors across various LRS being low to tilde operator 0.2%. The paper also discusses different experimental setups, including changing the setting from A to B and C, as shown in Table 3. These experiments demonstrate that the scaling law with LR annealing can still work well across different experimental setups. Furthermore, the study compares the proposed universal loss curve equation with other methods such as 1-sqrt and 1-square annealing, which are defined by H. Diaresis Agel et al. 2024. In Figure 20, the full loss curve fitting on cosine and constant LRS is presented, omitting the warm-up in the first 100 steps. The results suggest that the universal loss curve equation can accurately predict the trend of loss changes as LR varies. Similarly, in Figure 21, the full loss curve prediction, 120k steps, by the universal loss curve equation across various LRS is demonstrated, showcasing the precision of the equation in predicting the trend of loss changes as LR varies. The study's findings highlight the significance of the proposed universal loss curve equation in machine learning, particularly its ability to predict unseen LRS with high accuracy. The research contributes to the understanding of how different LRS affect the performance of machine learning models and provides a valuable tool for researchers and practitioners to optimize their models' training process. The research paper explores the scaling laws of learning rate schedules for large language models, focusing on the relationship between model size, learning rate, and the number of steps to reach the minimum learning rate. In Figure 22, the paper presents a curve-fitting analysis for cosine learning rate schedules across various model sizes, demonstrating a strong correlation between model size and the number of steps required to achieve the minimum learning rate. The fitted curve is expressed as loss equals 1.412 plus 0.921 s1 caret, 0.761, plus 2.562 n caret, 0.137, 0.069 d-sulfur mono-nitride caret, 0.117, with an R-squared value of 0.99837, indicating a high degree of accuracy in the model's predictions. The study also examines the effect of different annealing ratios on learning rate curves, as shown in Figure 23. The results indicate that both cosine and 1-sqrt annealing methods exhibit similar patterns, with the cosine annealing method displaying slightly more variability at higher annealing ratios. This suggests that the choice of annealing method may have implications for the stability and efficiency of the training process. The findings of this study contribute to our understanding of how to effectively scale learning rate schedules for large language models, which is crucial for achieving optimal performance in these models. By providing insights into the interplay between model size, learning rate, and the number of steps to reach the minimum learning rate, the research aims to guide practitioners in selecting appropriate hyperparameters for their models.